Hi, this is Ed from Wright. Today we're going to talk about belt drives. We oftentimes promote the merits of why we have two belts on most of our decks, or why we have all of our idler pulleys on the slack side with these setups. So today we're going to go under the hood of some of these things. We're going to talk about the physics and in the application, the things that we do specifically and why they matter, the materials that we use. We're going to go through this in detail, a little bit longer video. So if you're interested in those details, let's sit down and take a look. So first off, what is a belt drive and some of the merits there? You have a driver and a driven pulley, and you're transmitting power from one to the other. And some of the things that really make them great is they're efficient. There's a high level of efficiency between the driver and the driven. They're relatively inexpensive, especially compared to other types of drivetrain products. They're also low maintenance or no maintenance. You replace them periodically with very minimal tools and whatnot. There's an ability to change the speed ratio between things. So all of our engines run at about 3,600 RPM, but the mowers with shorter blades need to have a faster spindle speed in order to maintain the correct blade tip speed. So we have speed ratio control, torque ratios there. We can have multi-output, so there's one engine, but there's three blades. And those blades, because they're all connected together in that way, they turn at the same speed. One doesn't fall behind the other. The belts also serve as a fuse link, so if you happen to hit something with the machine, the engine doesn't instantly come to a halt or shear off any keys or anything like that. The belt slips for a second and takes some of that force. The alignment, you can have a deck that tilts from side to side or goes up and down relative to the engine, and the belt can take a certain amount of alignment. There's also dampening. There's an oscillation of the engine's power, and that gets damped out to the blades. If you have a really rigid drive system without any damping, then you can actually create a lot of chatter and fatigue in the drive as it's running. So there's a couple really good properties that make belt drives just fantastic. So let's get some specific about the words here. We've got this pulley, it's a V, it spins around an axle. Traditionally, they're called sheaves, some people call them shivs. Those words, and then we have pulley. They all mean the same thing. It's really more of just a language thing. In the Midwest, you'll hear sheave or shiv a little bit more than you do out east. And then if you have like pulleys that are for like a block and tackle or a crane or something, sometimes they're called a sheave more often than the pulley. A pulley for a cable is a little bit different than a pulley for a belt. A pulley for a belt, the belt will wedge in it and not touch the bottom of it, but a pulley for a cable has a rounded bottom here where the cable, the edges align it, but the cable actually rests in the half circle at the bottom. So you never want to put a cable in a belt pulley and vice versa. So the belt itself, it's a V shape. It wedges into the groove. There's cords generally in it. We'll talk about that a lot more in a little bit. And then you've got your drive. You have your driver and your driven. And then we have idlers, which come in all types of configurations, and there's some different words around that. So generally called an idler. Some people call it a tensioner, which is just as fine if it's being used for tension. We usually, when we just say idler, we're referring to a pulley that's on the back side or the slack side of a belt. You could also have a tight side backside idler. So if this driver is spinning this way, this is the tight side and this is the slack side. So this pulley here is on the tight side, sees a lot more force than a pulley on the slack side. We can also have V idlers. So these ones are on the back of the belt, so they're flat. And a V idler has a V-shaped groove, and it's on the inside of the path. So this one would be a standard configuration. We just call that a V idler. It's on the slack side. This, we would call it idler, if we're talking about it in a very specific way. We'd say it's the tight side V idler. Now, most of our drives are all like this. This is the way you really want it to be, as much as possible. So just a quick background and history on belts. How did we get to where they are today? They were never intended to do what we're doing with them today. But first off, starting back in the year of our Lord, they were using rope belts in the textile industry or thread to spin, bobbins and those types of things. And that evolved over the years to around the mid-19th century. People started using flat belts in factories. So you might across the factory, you have all these pulleys like this, and here maybe there was a steam engine of some sort, and it was driving the shaft across the top of the factory, and you'd have a machine center or something that needs power off of that main drive shaft as like a utility in the factory. When we got into the early 20th century, it started showing up in ag. Typically there you'd have a tractor and it had a wheel on it, and then over here maybe there was a bandsaw or something like this, or a threshing machine or something, and so belt would go down to it. Some of the neat things that could happen there is the belt could actually twist 90 degrees, or it could flip over to get it to spin the opposite direction. And those flat drum pulleys were actually slightly domed, and it causes the belt to center up. And if you would think that if you made your pulley a little bit like this, the belt would ride in the center, but it doesn't work that way. It tries to jump off right away. It's a slight backside curvature to them. They work really well, but they're really heavy and clunky. Around 1917, a fellow by the name of John Gates standardized the V-belt. And that was, today there's the Gates Belt Company, Gates Rubber Products, and they still make a significant amount of the world's V-belts. But that's when the concept first came out. In some of the earlier years, they were banding the belts together for some of these ag-type applications. But it was around the 1930s and 40s where small gas engines started to become a thing. And so the automotive business started using belts for things like an alternator and whatnot, and there was also small power equipment on the farm that was using these belts for those types of purposes. Now, also around that time is when we saw sort of a mass industrialization with tons of electric motors, and a lot of those had small V-belts in them. And originally they were called fractional horsepower belts, and today sometimes the category is still called that, but these belts that were really originally made for a quarter horsepower, we're now putting 30 horsepower through them. So the business has changed a whole lot, but there's a lot of the fundamentals that are still in place from the original belts of 1917. So how are belts made? In the factory where they make them, they have this drum, and they wind rubber around it, and then they will wind a cord of aramid cord or polyester cord on that for the belt, stiffening, and then some bottom layers and whatnot. So they make this drum that's made up like a cake of all the materials that the belt is made of, and then they cut or grind the belt V shape on the backside, and they cut them off separately from each other, and then they take them off, and then they inside them out so the V faces in, and then some belts are wrapped, and then the rubber goes through a curing process, a heat and steam type of thing, to cure and bond all those layers. So it's a very manual process. And typically, belts might be made 50 across on a drum in a batch, and the diameter of the drum is what sets the length of the belt. So the belt's construction, like I said, it's made up of layers, like the layers of a cake. We have the top cover. Sometimes that's a cloth material. Then we have the cords, and here I have a few pieces we can look at. So this belt right here, there's a cloth piece on the top, then there's some structural rubber, then there's gum rubber, then there's cords, another set of gum rubber. The gum rubber kind of soaks in and goes right around the cords to grab them. Then sometimes there's a fibrous rubber, and then sometimes there's a plain rubber, and then the bottom you might again have fibrous rubber or another piece of cloth. So this sandwich is made up of all kinds of things. Here we have a wrapped belt. You probably can't see necessarily in the camera here, but there's a fibrous rubber on the top. There's a black rubber that doesn't have fiber in it right where the cords are. There's a fibrous rubber right underneath the cords. Then there's this soft rubber down here, which is really just to line the belt in the V, and then it's wrapped in cloth. So there's a lot of different specs that you can have. You can actually have the cord at different heights in here. Some you'll have cloth or no cloth on the bottom. Generally, they come in sizes. So A might be what's traditionally considered as a half-inch belt, a 5L. This is a 5L belt here. It's about the height of an A belt and the width of a B belt. Then you have a B belt, which is a little bit bigger than an A belt. This is a B belt right here. It's common for a blade drive. A belts are common for pump drives. You've got 5V, which is not really that common in our business. You have C, which sometimes you'll see in more like farm type applications or on a combine or something. You'll see these larger belts that are about, I don't know if they're maybe 3/4 inch wide, something like that. You also have quote unquote mod belts. So actually this 5L is not conforming to the 5L specs. It actually has some modifications into it for this particular application that makes it last a lot longer. You can see how this edge is square and then this edge is tilted. And the cords are actually a little bit lower in there. So there is a lot of customization that can happen, and I'd say that all belts are not the same. So a A-section fan belt you pick up at the auto parts store generally won't last in a lawnmower hydro transmission application, because on a fan belt or an alternator, that belt might see 1 or 2 horsepower, but a lawnmower can pretty quickly see 15 horsepower in the hydro system or something like that. And they're not built the same. Now, even in the outdoor power equipment industry, there's belts that are Kevlar. So Kevlar is the trademark name for aramid cords. So that means that there's a particular cord in there, but doesn't necessarily describe the entire package here or what temperature limits the rubbers are set for and that kind of thing. In our world, a lot of our pump belts are very, very specific. We use premium rubbers that can run at much, much higher temperature. We've got some things in here to reduce cracking and improve flexibility. For example, this here, the cords are a little closer to the middle of the belt. So even an off-the-shelf 5L belt won't last nearly as long as this. You could put a B belt where you have a 5L belt, but if you took a standard Kevlar cord B belt and put it here, it's probably only going to last about 1/3 as long as this 5L belt with the premium rubbers in it. Now these belts, on our side, they tend to cost about twice as much, but as a service part, we tend to list them for around 5 or 10% more than a standard belt. So really you get pretty good value in there. Also, everyone hates replacing a pump belt, and so it's one of those things where it's worth the extra spec to have a pump belt last a really long time. Now belt length, this is something like pretty much everything in the belt industry it's empirical. There's a lot of equations and stuff like this, but there's always this like experience factor or K factor or something like this that is like sort of funny math. And so belt length, you can't take a tape measure or a ruler and measure the length of the belt. It's derived a little bit more indirectly. You can't take a flat belt, cut it, and measure it and get its length. You also can't measure the circumference of a belt that's laying on the table in a circle. Neither of those are going to give you an exact number. And the reason for that, part of the reason for that, is that if the cords are higher up in the belt section versus more in the middle of the section of the belt, if the cords are at the high side of it and you straighten out the belt, you're going to get a longer belt than if the cords were lower and then you straighten it out. So there's this neutral axis of where the belt is. And so how it's done is that there's a fixture that has a pulley or mock pulley kind of a thing on it, and apply tension to it. And typically on that fixture there's a little readout of what the effective length, we call it the effective length of the belt is. And there's standards in terms of exactly what those what that test fixture looks like. Now this effective length, it's usually within 1 inch or 1.5 inches of what you'd get if you put a tape measure around a belt, but it isn't the same number for sure. And it's not even a consistent adder. So it's a bit of a gamble if you measure a belt and then you go buy a belt that has that same dimension listed as effective length. All right, belt stretch. Now, a lot of us think of belts as stretching because you might have an idler that's positioned like such, or especially like an older tractor or something that doesn't have a spring idler on it. You set the alternator position to get that tension, and 10 or 15 hours later the belt's slipping. Well, what happened there is the belt didn't stretch. I mean, the cords whether it's polyester or Kevlar, especially Kevlar, these cords, the material properties are much like asbestos. It doesn't have the detrimental issues with these like the asbestos fibers do, but the material properties are pretty similar, and they're these fibers that are super rigid, and if you tug on them, it's like trying to stretch a rock. I mean, I think that's what I'm trying to say. The cords of the belt basically don't stretch. At the most, a belt might stretch 2%, and that's really a matter of some of those cords are twisted and sort of just straightening out a little bit as they settle in, but after that, they're not going to stretch throughout their life. It's not a ductile type material. So belts rarely stretch, but when we have that situation we perceive as stretch, really typically what's happening is the edges of the belt are breaking in and they're settling into the V of the pulley. Okay, the other thing is belt slippage while we're talking about stretch or tension. The idea that if your belt is loose, then your blades are going to be running slower, that's generally not the case. If there's any slippage between the belt and the pulley, that's more than just the natural amount of 1% creep or something like this, it's going to be squealing and smoking, and you're going to know right away. The belt is going to not last at all. So belt slippage is one of those things that's super obvious, because just recognize that you've got this engine that's 25 to 40 horsepower, and if it's slipping and the blades are like going a third of that speed, you're dumping 10 horsepower of heat. That's a very significant amount of heat. So you're going to see smoke and things melting if you really do have belt slippage due to lack of tension. All right, failure modes. First off, we have wear. In the outdoor power equipment industry, belts almost never wear out, where there's material wear. You might see wear if you have an industrial fan where there's electric motor spinning the fan. It's very low tension, and after thousands of hours, the belt starts to bottom out in the bottom of the pulley or something like that. That's wear. But in outdoor power equipment industry, we just really don't see wear. The exception that I've seen is our mowers generally have two belts. The belt that's on the right side doesn't see a ton of load because it's only spinning one blade. Sometimes that belt will wear out before it fails from the other failure modes. Now, you could also have tensile failure, which would look generally like a clean break. The impact, it could be from impact, hitting a stump or something like this. A tensile break could be a symptom of pulleys that are just really small. Pulleys that are small don't have a lot of leverage on the torque of the drive, so that could do it. Or the cord spec doesn't match the need. Maybe the cords are spec'd as pretty small, or there aren't a lot of cords across there. Maybe the cords are polyester when they should be aramid cords or something like this. So could be a number of those different factors. Just because there's a clean break doesn't necessarily mean it's a tensile failure. One thing about Kevlar is it hates compression. So if you have a belt that's slamming in and goes into compression, and that happens just enough times, it could later on result as something that looks like a tensile break. Now, just recognize that a tensile break, this belt, I don't know exactly, but this belt's tensile strength is probably somewhere on the order of 10,000 pounds or something like this. So when we talk about tensile break, it's a really significant number, and if it really is strictly a tensile break, typically you're going to see something else that bent, or damage to bearings, or weldment that something's mounted to or something. So you certainly can have tensile failure. Flex failure, this is where the action is out. This is why belts mostly fail in the outdoor power equipment industry. As the belt goes around a pulley, every time it goes like this, and then it goes around a backside, or it goes the other way, and it's just flexing back and forth millions and millions of times. It'll exhibit itself as cracks in the rubber. Eventually, we could have cord failure. It's just a natural cause, but it could be made worse by excessive tension or small pulleys or tight side backside pulleys. So if it's going around V pulleys every time it's flexing this direction, it's not so bad. If it goes around a big backside pulley that's on the slack side, it sees a little bit of back flex, but not that strenuous. Now, if it goes around the backside under a small pulley or a pulley that's under the tension side, it's really going to force it hard each way, and it could shorten the life by half or more, really, to have a tight side backside idler or small idler pulley. The other thing that causes belts to fail are cracking or chunking. This would probably be the second cause of belt failure in the outdoor power equipment industry. You might see on the inside V these cracks taking place. Those cracks can happen from flex fatigue, but it happens a lot faster if it's also pertained to heat. And if you have a piece of belt separate off the bottom of the V, that typically would also be heat related. And pump drives are known for being pretty hot, and so that's one of the things that we look at when we spec the materials that go into the belt, and the special rubbers that we sometimes use that can handle much higher temperatures. So why are belts so magical? First off, the cost. And they're around maybe a fifth the cost of a drive shaft. Both cost from a new standpoint, from a manufacturing standpoint, but also from a service standpoint. It's much less expensive to replace a belt compared to a drive shaft. I'm just comparing belts and drive shafts here because they're both things that typically a drive shaft coupled to a gearbox will give you a speed ratio and also allow the misalignment of the drive as the deck goes up and down. So that's why I'm comparing these two types of drive transfer. When you get into golf equipment, you might also have hydraulic drive, but in our world, that's not very relevant to what we're doing here. The other thing is you get a clutching effect or a fuse. So when things go bad, the damage is minimal and the service is not so bad. If you want to get a better sense of what I'm talking about here, just search for videos on truck pulling carnage. You know, like when a drive shaft goes out, it's a major event. And a lawnmower, the belt typically would slip and the engine would stall and nothing would go wrong. Or worst case scenario, the belt breaks and you put a new belt on it. So this clutching fusing aspect is really important. It does mean that a lot of the other parts of the machine don't have to be ridiculously heavy or overbuilt to support it. On the service side, there's generally no maintenance. You run the belt until it stops working, or through inspection you identify you need to replace it ahead of time. And then even then, there's no tools or minimum tools to replace the belt. The other thing we get here is speed ratios. We can get the correct blade tip speed, whether this is the long blades on a 72-inch deck or the short blades on a 42-inch deck. We can set that up so we get the peak blade tip speed with the same engine RPM. Alignment. So the deck can go up and down, and the deck can tilt relative to the frame of the machine. It's one great thing you get with a belt. But also misalignment very quickly shortens the life of belt. I think I forget exactly. Actually, by the way, right here I've got this book. This book is just phenomenal. It's the Machinery's Handbook. It's the 27th edition. I think they're up on the 30th edition or something now. This book is about 100 years old. And this book, if you really read through every page of it and take the time to understand what they're describing, this book pretty much is a degree in mechanical engineering. Really good if you're interested in building things or you want a free degree in mechanical engineering. Get yourself one of these books. They're not cheap. They're like $100. But in my younger years, I grew up reading through this thing backwards and forwards and just have learned a whole lot from it. It's just super. But anyways, what was I saying here? So I think the rule of thumb for misalignment is, I think 5 degrees just about halves the life of your belt. The next 5 degrees even worse. So misalignment is really hard on a belt, but we use it because it works, and it works generally pretty well if you manage all the factors pretty well. Now, belts are efficient. They run at about 96% efficiency. So if you put 100, whatever in, you get 96 out. Horsepower we generally aren't going to run 100 horsepower through one of these belts, but if you were, you get 96 horsepower out. That's pretty efficient, all things considered. Now, the idea that a drive shaft and a gearbox is going to be more efficient generally is not true. Typically, a drive shaft has one bearing to hold one end of it and a belt from the engine to that stub shaft anyways. So you have the 96 times the loss that's in the first bearing mount. Let's just draw it. So you may have an engine spinning this. You've got a bearing mount here. You've got the drive shaft with the adjustable sleeve coupler in the middle, spline shaft. You've got the U-joints. You've got a gearbox, and you've got a second pulley. So the idea that running a deck off of a drive shaft is more efficient generally is not true, and because you have two belt drives when otherwise you may have just needed one to get to this point. And all you have to do is put your hand on that gearbox and you'll feel that it's hot. And that's just evidence that there is an efficiency loss there. So there's times and places to use a drive shaft, but generally it's not in order to achieve efficiency. All right, so what makes a good drive? Some of the things that really add life are big pulleys. The bigger the pulley, the more leverage it has on that shaft. So if we want 1 foot-pound of torque and the pulley radius is 1 foot, we put 1 pound here and we get 1 foot-pound of torque, and that reaction is on the shaft. Now, if we make that 2 feet, we only have to apply a ½ pound of force, and so there's a ½ pound of force on the bearing on the shaft. So when you make your pulleys big, everything else gets much, much happier. You have a need for much less tension, you have less fatigue and flex in the belt, you have less load on your drive shaft or your on your spindle bearings. Also, another thing that we do, whenever possible, we try to set up our belts where if we have the drive shaft, we'll take the pump belt and pull it opposite of the deck belt so that we cancel out the force that's on the engine's crankshaft. Engine crankshafts typically don't have wear issues, but if you frequently start an engine, it's a journal bearing, and there's a little bit of grinding that happens right before the oil pressure builds up. So we try to keep those loads balanced on the crankshaft. Big idlers are really important. You get less back flex on the belt, which is the hardest flex on it. And also we want those idlers on the slack side. We want no tight side backside idlers to reduce flex. The other thing we want is lots of wrap, less tension required. I think I have this one listed here twice. If you look at this diagram right here, let's say this is the engine, these are two pumps. This engine pulley's doing 100%, these are both at 50%. Well, this here has almost 180 degrees of wrap. In this example over here, maybe that's 190 degrees. This example over here, we might have 160 degrees of wrap. So anything we could do to increase the wrap around a pulley will increase the amount of traction it gets, and therefore decreases the amount of tension we have to put on it to make it work. Alignment is important. We want less wear on the edge of the belt. Many of our machines, the engine actually goes up and down with the cutter deck to keep that 5% half-life factor out of the equation. We have other machines where we have an integrated transmission on the mower, so it's not really so much an option to move the engine. And we're doing what we can to give the longest run from the belt, from the engine clutch to the deck, to reduce that misalignment, but it's a reality, and the belt is the least expensive of all the components involved in there, and the most flexible. Now, do note that if you have a machine with a floating deck like that and you cut every day at 3 or 3.5 inches, you have very minimal or no misalignment, so it's a non-factor. It really becomes a factor if you're trying to cut at 5.5 inches, or maybe down at 1 inch or something like that is where you get to the limits of that situation. I talked about the counteracting loads on the shaft, so especially the engine, we try to get the two belts to be pulling opposite each other. The other thing to keep an eye out for is serpentine belts. Serpentine belts have some particular challenges in a lawnmower type application. They're great under the hood where you're driving an alternator or something like this, and you can machine all the surfaces that everything's mounted to. They're not weldments, that kind of thing, because you can get perfect alignment. If you have a serpentine belt, and just what I mean by a serpentine belt, it's a micro V. So you've got this smaller pulley, and there might be 10 little V's across the top of it. It's generally a little pulley like this. And oftentimes in an engine under hood application, you're going to see that go around many pulleys. But they can get the alignment perfect in an application like that. If the misalignment is a little bit off, that belt will get destroyed really quickly. The other thing is typically those pulleys are really small. And so in order to get that same amount of torque, there's tons of side load on that shaft. And so it becomes possible to break the shaft off a spindle or a shaft off a pump, or significantly shorten the journal bearing life inside the engine because of the small pulley. The other thing with serpentine belts is they have a real hard time eating sticks. So junk goes up in the drive, and it has to, not be destroyed. And serpentine belts just are not good at that, whereas your larger B belts will generally just chew up stuff that goes into it. The other thing is harmonics. So a good belt drive is going to not have bad harmonics in it. So that's when when the belt's running, the belt can sort of flap. If it's flapping a little bit, it's not that big of an issue, but if it's at the wrong frequency, at the wrong load condition, it can jump off the pulley. And oftentimes the temptation is to increase the tension, which sometimes changes the harmonic to a higher frequency so that it's not happening at that speed, doesn't happen as much. But also note that if you decrease the tension, you also move the harmonics to a different point. So a lot of manufacturers, what they do is they increase the tension in order to get some of these harmonics to go away. Now, we've done few things that I think I would say are trade secrets to reduce our harmonics and therefore allow us to significantly reduce our belt tensions while keeping the belts on. And our belt drives are also generally designed to allow for you to engage the clutch at pretty much any engine RPM. That's not the case with a lot of drives. A lot of drives, if you engage the clutch when the engine's at an idle or 1/3, the belt might jump off. Certainly it can happen, but we do all that we can to get to the point where at least 99% of the time it doesn't jump off if you engage it idle. In terms of what speed to engage your engine, I'm a big proponent of saying that you should engage your clutch with the engine at full speed. It's not the best on the clutch, but you're turning time into money with these mowers, and I wouldn't be throttling down every time because it'll take you more time than you'll save in money. And also it's a little smoother on the belt to engage it at full speed. So takeaways, look for low tension drives, look for large pulleys, look for tight side backside idlers. That's a bad sign. You don't want to see that in there. You don't want to use a fan belt as a replacement. You want to be sure that you're either using the OEM belt or you really understand the belt that you're buying and you know what you're getting into, or you've tested it or whatever, and you know it to be sufficient. This is true for all the belts, but it's especially true for your pump belts. Not all pump belts are made the same, and generally the OEM belt, and this is across brands, it's not just with us, but generally the OEM pump belt's going to be a modified belt for the application and could increase the life by 2-3 factor of a fan belt type thing. The other thing to do is replace the belt when you see cracks. Belts are a perishable item. They're going to fail at some point. And if you wait until they break, then it's going to leave you on the job site with a machine that can't move under its own power. And so that's because that's inconvenient. It's a lot easier to do it preemptively, especially in the wintertime. Belts generally don't fail quick. They give a lot of signs before they fail. So they're pretty easy to look after from a preventative maintenance standpoint. Things like a bearing, those are much harder to detect when they're about to fail than something like a belt. So they give you the signs. If you listen to the signs, then you'll never be stuck on a job with a lost belt. So hopefully that's helpful to you. Some of the physics behind the belts, why some of these factors matter, and what you can do to get the most out of your machine. When we approach this topic and how we've looked at it over the years, what we're looking for is doing what we can with the materials available to give you the best return on your money, which is your ability to turn your time into invoiceable jobs. So that's uptime. Our goal is to give you as much uptime as we can, and we try to give you an affordable machine, but we will spend the money on the right materials if it means you can turn your time into money more consistently and at a faster rate. Anyhow, I hope you have a great rest of your season.